With work and energy review. The first little bit of this note is just going through types of energy that we discussed last year. So kinetic energy was maybe that, and gravitational were the two biggest. So just remembering some of the details. Kinetic energy is energy due to motion, and so it's related to speed. Okay, we give it the symbol usually EK, though sometimes out of laziness I'll do KE, whatever instead, but the proper symbol is E with a subscript K. Like all energy and work, the units are joules, J. And in the formula here, pretty simple, but mass is in kilograms and speed has to be meters per second. Gravitational potential is, like I said, it's the idea that if you lift something up, it has potential energy because it has the ability to do work. If you let go of it and it falls, it has the ability to speed up, and that by definition is work. So that's why it's called potential energy, because it's sitting up there. It's not really doing anything, so it has not got kinetic or thermal energy, so to speak, but it has the ability, the potential to speed up. Anyway, so the symbol again, E subscript G, excuse me, sometimes out of laziness, GPE. The formula is just MGH, where mass is kilograms, G is 9.8, and H is height. Okay, and once again, the units are joules, J for joules. Thermal energy we talked about last year, and this is specifically if you have a system where there's friction, as all systems have, but we sometimes don't assume there's friction. But if we're assuming there's friction, then we count thermal energy is the amount of energy that got lost due to the friction. Like, I don't mean lost, it just means it's heat in the area, in the air nearby, right? It warms up air molecules or the substance that where the friction's occurring. But the object in the example I might give might be like a hockey puck on the ice. There's a little bit of friction there that'll cause it to slow down with time, and so there's energy, kinetic energy, lost from the hockey puck, but it's added to the ice nearby. Okay, so this is the big one. This is the important thing from last year. It's not what the energies are, but it's how the law of conservation of energy, that energies just always transform from one type to another. Something that's kind of cool about relativity, like Einstein's relativity, that we do not consider, is that mass and energy are equivalent. And of course, that's Einstein's famous equation, E equals mc squared. There's an equivalence between them, and mass can become energy and energy can become mass, which kind of screws up this whole law of conservation of energy. Fortunately, from a practical point of view, this works just fine, and we will use it all the time. So the formula, and I always want you to think about the formula, right? And how it's developed. You say the total energy, ET1 means the total amount of energy that you had before something happened. So my example would be the total amount of energy of your tennis ball as you're holding it above the ground. It's got a certain amount of energy, and that's mostly going to be gravitational, right? It's not moving. And then if you let go of the tennis ball and it accelerates towards the ground, then some of its energy, then it's got, after it accelerates for a while, you might call that ET2, that time, after that time it accelerates. So that's the second time. And the energy is constant. It's just a matter of, it might be different types and different quantities. So it might have a little gravitational after it's fallen for a bit, but it's got some speed. And for some reason you wouldn't, but if for some reason you calculated the thermal energy lost, there's some there too. There's always thermal energy. We just don't usually always calculate it. Certainly there's lots of other types of energy you could include. This semester, this unit will add spring energy, which wouldn't apply in the example I just gave of a tennis ball, unless you're counting the bounce, but let's not get into that. And then later on we'll talk about electric energy as well. But right now, the only types we used last year were these types right here. Okay, so here's a big example, but this is exactly the sort of question we did last year, so it's important to have a good concept or a good reminder of how to do this, because we will apply these types of equations. And in your next assignment problem set, there are some that are just straight from this example. So you got a roller coaster, and we know its mass. We say, okay, it's coming over the first hill. Here's my picture. So here's the first hill. And it's got, we know the height of it, and we know that over that first hill there's its speed, okay? We know the height from the ground. Then it says, find the kinetic energy at the top of the first hill. Well, for part A then, we'll worry about other stuff after, but for part A, it's pretty simple. You just say, all right, well, kinetic energy is 1/2 mv squared. We know the mass of the thing. We know the speed of that first hill, so it's a very simple calculation. Again, what's a reasonable number? I don't know, but that number makes sense from the context of the numbers we're given. So we'll just go with that. Okay. Part B says, okay, goes down the first hill and through the loop, ignoring friction. Oh, we're happy when we can ignore friction. Calculate the speed of the train at the top of this loop. Okay? So, just looking again at the situation then, we're saying, okay, there's 21.3 meters off the ground, and there's 50. That doesn't look like it's drawn to scale, but that's okay. And we want to find the speed right here. So our V1 is on the top of that hill. It's got a little speed. It's got lots of gravitational energy. And our V2 is at 21.3 meters. And here I make the note about usually when you're looking at a question and you're comparing, you want to say your lowest height is 0. So this one, it's 21.3 meters. But it's nice if you can just say, well, let's call it 0. And then this H will be the difference between 21.3 and 53.2. You don't have to do that. It just, sometimes it's easier. Just one less thing to calculate, right? So let's look at the solution. Yeah, best form. Start your problems when they're related to conservation of energy with ET1 equals ET2. Then you list all the types that you have. In this case, we're not dealing with anything new yet. List the formulas, right? This is a great communication bit to start with. We're looking for V2. Yeah, so let's just look at my givens then. So if using the heights in the diagram, then there's an EG2. If instead you use H1 is this, that's what I was saying earlier, then we can call EG2 equals 0. So if you say your H1 is just the difference, then you can say EG2 equals 0. Let's just look at that to make sure it's clear. So saying, first of all, H2 is relative to this point right here at 18.59, and H1 is 54.49. So if I say this height is 0, then this one's going to be the difference between the two, the 30, 31 meters or whatever. Okay? So it said ignore friction, so we can call this 0, which is nice. And you can just see I start to sub in numbers here. Notice that every number has to be every term. I know we're given a mass, but the reality is, because every single term, there's a term, there's a term, and there's a term, all three of those terms have an m in it, I can just cancel them right out. I'm just going to do that right now. I'm going to cross them out. We don't need to use them. We'll just cross them out of the equation. And then you can see in the further down here then, when I isolated V2, and I know that's a big step, and I'm not showing all the steps from going from here to here. That's sort of the thing that I hope you can sort of work out on your own. If you need help with that, you know you can ask me in class, but it's just rearranging from here to here, just getting V2 by itself. Okay? Then you can work through the numbers, and hopefully, if you're doing it with me, which would be great, you get 25 meters per second, and I'll check mark that. I'll check mark it because it makes sense. 25 meters per second, which is times 3.6, let's say times 4, just under 100 kilometers per hour. So at the maximum, actually that's pretty fast. 25 meters per second on that loop, that'd be pretty fast. But we ignored friction, so we can do that. And then, yeah, we won't get into it right now. But of course, you could start looking at centripetal force, what speed it would have to have, and all that sort of thing, but we're not doing that. Part C, obviously pause if you need to be writing right now, but I'm going to switch the screen. Part C says, before applying the brakes at the end of the ride, so down here, the train moves along a level stretch 2.71 meters off the ground. This is what this is. The train speed is 24.3, so we know the speed right here, and we want to find out how much of its energy went to thermal energy. So it says, where does it go? Well, it's I guess I gave the answer away there. Obviously, it's thermal friction, right? So what we're going to say is if we know the total energy here and the total energy here, the difference between the two will be thermal, right? So I'm going to scroll down again. So we're looking for E thermal. just looking, important to acknowledge what data we have. So we're going to call V1. We know V1 is the initial speed. We know the initial height. So this height is relative to, I'm going to scroll again, so just wait a sec. Just looking at the heights. So this is, originally we were told the height was 53.2 meters off the ground. So this H1 using 50.49 is a difference from here to here in height. Okay? So we know the height. We're saying that H3 is 0. We know the speed, and then we just solve for E thermal, right? So here's the equation. Again, good form to write it all out. Write out the numbers. Isolate E thermal. Notice that I took EMGH3, took it out because H3 is 0, right? So this term disappears. Rearrange for E thermal. And sub in the numbers. And you get a giant number. And is it reasonable? I don't know. That's a hard one to say. They usually are. E thermals on something like a roller coaster are usually huge numbers. Notice, by the way, in this one, I couldn't just cancel out the m's because I have 1, 2, 3, 4 terms in this equation, and this one doesn't have an m in it. Okay, so I couldn't cancel out m's. I have to sub them in. Okay, so you might want to pause to get that written down, but again, I'm going to scroll down and past. Oh, and the energy is lost to heat, which we talked about. Okay, so again, if you need to pause it, please go ahead. But I'm going to move on to the next example. And I like this one. It's not Charlie, but it looks like him. Certainly Charlie's been stuck going down slides before. This isn't the first time. This could be Charlie. Mass of 12 kilograms for Charlie. I think that's ambitious for him. Is going down the slide. He's starting at rest up here. The slide is 3 meters above the ground, and we know the incline angle of 40 degrees. So we want to find out how fast he's going at the bottom, knowing that this is the coefficient of friction between his butt and the slide. Okay? So, drawing out my picture, the things that I know is the slide height is 3 meters above the ground, and we know the incline angle, and we're looking for V2. We're going to say, it says here that when he reaches the bottom, which is 0.5 meters above the ground, so that means that right here, he's 0.5 meters above. So I'm going to say that given making that 0 makes H1 2.5 meters. Okay? That doesn't immediately make sense. Take a moment with it. And then, of course, we know the coefficient of friction on the slide. We don't know what distance he's on the slide for, but we can figure that out using trigonometry. Okay? So, again, we're looking for how fast is he going when he hits the bottom. So just looking, I just wrote out some of the formulas. E thermals, kinetic friction times distance down the slide. We know that kinetic friction is normal times mu k. We remember from last unit that normal is mg cos theta. So therefore, it's a mouthful, but that's what E thermal is. Mg cos theta times mu k times delta D. Okay? You might want to take a moment and think that through if I went through that quickly, but this is just saying, you know, these are just straight formulas, right? Knowing that Fn is mg cos theta, and then E thermal is this whole bit times D, so I had to throw a D at the end. Okay, to solve for D, just use trig, where you say, I have the opposite here, so 2.5 over D would be sine of 40, and then solve for D. Okay, so the length of the slide is almost 4 meters, 3.89 meters. So that was sort of, we had to figure that out before we can even start the conservation of energy part of the question. I'm going to scroll down here. So looking then at the conservation energy part, looking at the data, well, we know Charlie's mass, we know he's starting at rest, we know the initial height, his final height you assume is 0. We're looking for V2, we know the kinetic friction coefficient, and we know how long the distance of the slide is. So just looking at the right, this is the standard stuff. These two lines, just copy and paste and they never change. Actually, these 3 lines, right? That's a great start. Then you start saying, okay, what's 0? What don't I have to count? Well, since H2 is 0, then this must be 0. So you can cross that right out. 0. And since V1 is 0, then this term is 0 because he's starting at rest. So he's got, the idea is that gravitational energy turns to speed, kinetic energy, plus heat. That's really what's going on here. Okay? And we're going to calculate that by subbing in the numbers that we know, m times g times 2.5. This is what we're looking for is V2. I left the m's, even though we know his mass is 12, because, once again, there's 3 terms in this equation. Oops. 1, 2, 3. All 3 of them have an m in them. So I can cancel out the m's. See ya, and see ya. Okay? So now subbing in the numbers, and we want to find V2. Oopsie, and we're looking for V2. So at this point then, it's just a rearranging and solving for V2. It's amazing how, you know, rearranging this equation for someone in grade 9 would be like devastatingly difficult, right? And for you now in grade 12, it's like that's the, I call that the dot, dot, dot. In university, there's stuff the university professors goes through all the time. They go through these super hard questions, and it seemed like they'd stop. They'd write like this line here, and then they'd go, okay, dot, 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 and assume you can do the rest, which is sometimes frustrating. So if you feel a bit frustrated by me just saying, okay, from here, V2 is this, you know, I understand, and I'll help you with that in class, but I just don't want to take time on the videos for it, okay? Dot, dot, dot. Anyways, 5.9 meters per second for poor Charlie at the bottom of the slide. That makes sense. A reasonable number. Okay? And yeah, that's it for conservation of energy. So you will find that you can do a good part of your first assignment already. Problem set number is at 5. Problem set 5 using the stuff that from last year. Probably 3 or 4 questions are just straight out of last year. Okay? And then you need to get into springs, which is the next video. That's a long one, eh?